Welcome to our last geometry YouTube video. Given everything that's happened, obviously remember that next week is just a catch-up week for people just to finish those things. We will not have anything in geometry as we got through all of our stuff after this. These are our last two lessons, but they're both pretty short with 3 examples there and 2 examples in 13-7. So with that being said, let's get right into it. Otherwise, we will have a Chapter 13 review optional assignment that will purely just be extra credit points. So for those of you who didn't exactly get the type of grade you want on your homework section, that's where that could be making up some extra points. Okay. So first, 13-6, conditional probability formula starts on page 856. Now this section, the example problems are all pretty wordy, so I encourage you to follow along in your book. I'm going to have abbreviated words on here, but just so you don't get lost, that's something you could do. Okay. So first, we need to talk about what the conditional probability formula is. So, the probability if B given A equals the probability of A and B over the total probability of A, given that the probability of A cannot be 0. Okay, so that should look pretty familiar with last week, where first of all, we need B to exist if A exists. The probability of both is what we're looking for, over the total probability of A in general. Now this probability of A cannot be 0 seems interesting and weird and random, but really it just means anything we've had before in math. If probability of A can't be 0, it means our denominator can't be 0. So obviously we can't divide by 0, so that's just cleaning that up. A has to be possible, because if A is possible, then B and A can't happen, and it's all a mess. Okay. So that being said, let's get right into an example. Example 1. We're going to use conditional probability. Use conditional probability. Now again, I encourage you to get out your book because again, these are wordy things that I'm going to abbreviate because you guys don't want to sit here and watch me write down the whole problem for 3 minutes. So, in a study, half of the volunteers received the test drug. So let's see, half received test drug. Okay. Which means that half received a placebo. Okay. Those of you who don't know what a placebo is just a fake drug. You have to do it during studies just to prove that your drug's actually working. Because the crazy thing about these drug studies is if you think it's going to work, often it'll work anyway, regardless if the drug has an effect. So you have to have a placebo. It's called the placebo effect, where your body gets better even though there's no reason for it to. It's often just sugar pills or water pills. Okay. The probability of someone who received the drug, who received the drug and got better, was 45%. Okay. What is the probability someone got better when they received the drug? So, probability, got drug, got better. Now, I'm sorry, you would think that 45% based on how I read it, but of the people who got the drug and got better, 45% of the total. Okay. So 45% of the total people got better when only half of them got the drug. So again, I need to look at my conditional. So first, what is the probability of A and B? Well, A and B, A would be, did they get the drug? And B, in this case, would be if they got better. So, because A has to be the event that happens first. So, the probability of A and B was when they got the drug and they got better. So, what would that be in this case? Well, they got the drug and got better, that'd be 45%. Now instead of writing 45% as 45%, I'm just going to write it as a decimal. So that would be 0.45. So that would be that one, A and B. Now we also have to consider just the total of A. Again, any probability, we have to take it over the total. In this case, total of A, which as we said was just to get the drug. Well, how many people got the drug who were tested? I'm sorry, how many people in the study got the drug? Well, that would naturally be half, or as a decimal, 0.5. So I get 0.45 over 0.5, and I could just divide that out, and that would be 0.9, or 90% of the people who got the drug got better. So it's a very effective and good drug. Now all you have to do is consider the side effects potentially. Even though I've basically done a chapter and a half on here, or 2 chapters, it still feels weird not being able to ask you guys for questions. Okay. Example 2. Compound conditionals. Okay. In a survey of pet owners, 45% own a dog, 27% own a cat, and 12% own both. Okay. What is the probability that a dog owner also has a cat? Okay. So again, I would set this up as probability of A and B over probability of A. As you said, what's the probability they have a cat if we know they have a dog? Probability cat if dog. So, what's the probability that they have both? Well, as we said, both, it would be 12% or 0.12. Now we are comparing it to which term? Which one was the prerequisite? Well, the prerequisite, as I said, was that dog value, so 0.45. And again, I can just type that right in my calculator. 0.12 divided by 0.45, which is 0.26 repeating, or let's just say 27%. Just because it'd be 26.6 repeating percent, 27 is fine for me. Okay. Now, sometimes we're not always looking for that exact value. So let's go back to our formula and just sort of consider some algebra here. So if the probability, oh, like this one's not very good. That's not very good either. Oh well. Okay, so these last couple problems, we've been given these 2 pieces of information and we've solved this, which is easy because again, whenever you're trying to solve for something, you want to isolate that value. But what if I had something like where I was given this value and this value, and I was trying to find the probability that both were to happen. So let's say we throw in some numbers. Let's say the probability of both would be like 0.6, and then we're trying to find the probability of A and B, but we knew the probability of just A was 80%. Well, any algebra was saying was to get this variable by itself. I know it's a lot, but it's all one variable. It's probably it's just a p. It just has some subtext to label to it. How would I get rid of that 0.8? Well, I'd multiply by 0.8 to each side, right? And I can take 0.6 times 0.8. So in this case, 0.6 times 0.8. P of A and B would be 0.48, just multiplying them together. So the same logic holds when they're just variables. If I'm just trying to isolate this value, I can multiply by the P of A, and I get rid of it, which means I have to take this value times that P of A. So again, just algebra, just plug in what you know and try to do some algebra to solve for what you're missing. So, we're going to actually take that into consideration and do it with our next example. Let's see. Example 3, using a tree. Probability tree. Okay. So, let's see. 70% of college freshmen went to a public high school. Okay. 60% of those, let's see, how do I want to write it? Of public high school kids graduated within 5 years. Now, it doesn't mean they graduated high school in 5 years, it means they graduated within 5 years. So within 5 years of graduating high school, so for example, I graduated in 2013, okay, boomer, and I didn't go to college until 2018, well, I would still be within that 5-year stretch. Okay. And 80% of private high school graduated in 5 years. So, same thing. That's the other value. So we're actually, we're given a lot of information and it seems pretty goofy. I know you're probably going, Mr. Lane, 70 plus 60 plus 80, that's over 100%. And I would go, I agree, that's true. But what's happening is some conditional probabilities. That's why we use what's called a probability tree. Now, a probability tree is, well, it's exactly what it sounds like. You just break things off into branches. So first, we need to figure out, do they go to a public or a private school? So let's do public or a private. And I'm going to do boxes. And we need to connect it to something, some base, so they're all college freshmen. Okay. So, how many of them went to a public or a private school? Do we know that information? Well, we do. We know 70% of public freshmen went to a public high school. So, 70% went on this path, or as a decimal, 0.7. But if 70% of freshmen were public, how many had to be private? Well, again, logic would dictate that would be, the remaining percentage would be 30%. Alright, technically in the book it says non-public, which means it also factors in homeschool kids. I apologize for not including that demographic. We're just going to have private count as private high schools and homeschool kids and alternative college or high school preps. Okay. 60% of public high school kids graduated in 6 years. So, again, I get branches in 5 years. And then, of course, we get not in 5. And, of course, 60% of them graduated in 5 years, so I get a 0.6 here. And then here I will get a 0.4. We only worry about the percentage of that particular branch. So the 60% isn't 60% of the whole, it's just 60% of this public school kid group. And the private is 80% graduated in 5 years, so in 5 years, and then not in 5. So in 5 years we had 80% or 0.8, and then the remaining would be 0.2. So this is what's called a probability tree. So we did all that, we need to find it, we need to have a problem to solve. So the problem to solve is, what is the percent of freshmen who graduated in 5 years? Okay. That would be the percentage of total freshmen. But do I have a branch of total freshmen who graduated in 5 years? Technically I don't, because this group graduated in 5 years, which would be this branch. But are they the only group that graduated within 5 years? Which again is no, because this group did right here, which would be this path, this path. So we need to figure out a way to figure out the total number of freshmen in general. Well, again, using that idea earlier where we have the probability of B if A equals the probability of B and A over the probability of A, we can sort of do some figuring. Well, let's just worry about the public school kids first. Okay. Well, I don't know the percentage of them doing it both, but I know the percentage of B if A, how many kids graduated if they did public school. We said it was 0.6. Again, we don't know this probability yet of the total who overlapped, but I do know how many kids went to public school, 0.7. So I can just multiply 0.7 to each side. And I'm going to get 0.42. So that value I'm going to get is 0.42. But like we said, we need to find the probability of public graduate, and we also need to find the probability of private grad. And how can we find the probability of everybody? Well, with those two numbers, we are going to add them together. Because the probability of them graduating school, we just need to lump them in those categories. And colleges do stuff like this all the time to sort of figure out where they're getting their incoming freshmen, all that stuff, so they can better prepare. And obviously, high schools do the same thing, where they see the percentage of their kids who go off and how they can better prepare them, especially private schools. Private schools do that all the time. Okay, so doing the same process, what is the probability that someone will graduate if they went to a private school? Well, as you said, that was that 0.8. I don't know the overlap just yet. But what is the probability that they went to private school? Well, 0.3. And then how could I get that 0.3 out of there and this myself? Multiplying by 0.3 to each side. So I get 0.8 times 0.3, which would be 0.24. So 0.24. And then of course I can just add those values together. So 0.42 plus 0.24 would be 0.66 or 66%. That one was a little tricky. Double check the book, make sure I did it right. Yep, all good. And I'll give you a chance to write that down here. And that is it for 13-6. So we'll go right into 13-7. But we're going to skip the first two examples because they're kind of silly and I don't really like them. Now we're on to 13-7, modeling randomness. It's on page 862. Again, wouldn't be a bad one to look in the book, but one of the examples is wordy, but it's fine. Okay. So the way we do this, modeling randomness, is what's called expected value. Okay. Expected value is the sum of a value of all our values times their probabilities. Okay, so the value, sum of values times their probability. So it sounds really goofy, but let's do a very easy example, and we're going to calculate the expected value of one six-sided number cubed. Or again, 8 times. So the sum means we're going to add them all together, and their values times their probabilities. Well, if I roll a six-sided number cube and I roll a 1, my value would be 1. So if I roll a 1, what is the probability I would have rolled that 1? Though? That would be 1 in 6. I also have to do the if I roll a 2, what's the probability I can roll a 2? Well, again, 1 in 6. How about a 3? Well, again, 1 in 6. I can roll a 4, again, 1 in 6. I can roll a 5, I have a 1 in 6 chance of doing that. And I could roll a 6, I have a 1 in 6 chance of rolling that. And then again, the sum, so to add up all those values together at the end. So I get 1 times 1/6. Well, that's just going to be 1/6. I get 2 times 1/6, which would be 2/6. 3 times 1/6, which would be 3/6. You could simplify these down, but I'm going to keep them all the same just so I can combine them at the end because I'll have common denominators. 4 times 1/6 is going to be 4/6. 5 times 1/6 is 5/6. And 6 times 1/6 would be 1 or 6/6. Now all I have to do is add them. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. 21. Okay, 21 over 6. And now here's where we can start to simplify stuff down. So let's see. Well, we can divide each by 3. I get 7 over 3, and then that's a calculator thing. Oh, 7 over 2. So that would be 4.5. 21 divided by 6. 3.5. Math. I was going to say 4.5 sounded really, really high. Yes. Expected value. In fact, I actually use this type of idea a whole bunch when I'm playing Dungeons and Dragons. Just so I can figure out how much damage I need to do so I can kill something. Or if I can hit something, or I can pass an ability check. Yeah. Expected value. The sum of all possible values times their probabilities. This only works, again, in pure randomness. So we're going to do an example. We're going to make it random by eliminating all skill, but in theory it wouldn't be completely random. Let's say we're throwing darts at a square board. Now again, that would be a skill thing, or a skill thing would influence that. However, we're going to assume you're a complete amateur and you have just as high probability of hitting the bullseye as you do anywhere else on the board. So, example 3, expected value. We're going to find the probability, or the value. Okay, so let's see. We have a big old thing here. We have a medium one. Then we have a smaller one. Okay, so if you land in the black, you get -5 points. And the total area would be 432 inches squared. Okay. let's see. If you land in the red, you will get 10 points. And that has an area of 108 inches squared. And then if you land in the blue, that is going to be worth 20 points. And that has an area of 36 inches squared. I gotta double check something quick, just so I don't mess it up. Okay. Alright, so we have our value. Remember, expected value, we just do our points times probability. And then we add them all together at the end. Now, how do we find probability? We need to find the possible chance of it happening. So we would find our area, the chance of our area over the total area. So I need to find my total area. How can I find my total area? Well, I can just add each of these three areas together to find the total area of the board. So 432 plus 108 plus 36. 432 plus 108 plus 36. We get 576 inches squared. Okay. Now again, expected value. We just need to take our points times the probability that's going to happen, add them all at the end. So, if I land in the black, how many points do I get? Well, I get -5. Now, what's the probability of landing in the black? Well, that would be my 432 over my 576. Again, probability of just being that chance over the total. Okay. 10 points, my probability would be 108 over 576. And then of course my blue, I get 20 times 36 over 576. Okay. Well, I can just type some of those things in. So first, -5 times 432 divided by 576. Of course it shows off right away. Okay, -5 times 432 divided by 576 gives me -3.75. Alright, now I can do my red one. 10 times 108 divided by 576 gives me 1.875. Then of course I could do my blue, which is 20 times 36 divided by 576, which is going to give me 1.25. Now, to find my expected value, all I have to do is add those together. So, -3.75 plus 1.875 plus 1.25. Okay, so overall, my expected value would be -0.625. So I'm expected to lose. I'm expected to lose points. So the question is, should I do it? No. In fact, this is often another example of why you guys ever hear the house always wins. I know you guys are children, but in gambling, casinos do this process all the time. They're comfortable giving out these big payouts when they're so unlikely that at the end the customer is supposed to be at a net loss. They're supposed to lose so the casino can make money. The casino doesn't do any good if it loses all its money. And then we're going to do one more thing here, and that'll be it. That'll be it for geometry. example for make decisions. You are all now football coaches. Let's go kick a touchdown. You're all monster. Okay. So it is 4th and 1 on the goal line. For those of you who don't know, the goal line is right before the end zone. Okay. You have a 90% chance to make a field goal. It can't be 100% because I'm sure a lot of you are Bears fans. And you have a 35% chance to score a TD. And we are going to assume that you make the PAT. PAT is point after touchdown, so what it means is score. Okay, so we need to look at this objectively. 90% chance to make a field. I'm pretty sure they count the PAT automatically. Let me double check that. They do. Okay, they do count the PAT. Okay, 90% chance to make a field goal. So, first, how much is a field goal worth? Well, a field goal is worth 3 points. How many is a touchdown plus the PAT worth? Again, we're going to go with 7 points. Now, in this case, the expected value is kind of goofy because you can't do both. You can either do one or the other. So you have to make a decision which one you think you should do. So, what would be my expected value if field goal? So, how many points would I get for a field goal? Well, that would be 3. And what's the probability I have of making it? Well, 90% or 0.9. So I get 3 times 0.9, which would be 2.7 points. Okay. Now, I can do the touchdown. Expected if TD. Again, I would score 7 points, and I have a probability of 35% or 0.35. So I get 7 times 0.35. I don't know, 7 times 5, which would be 2.45 points. So, in this isolated incident, which one should you choose? Well, you should always choose what gets you most points because, spoiler alert, when you score more points in a football game, wins. So, your decision would be that you should kick the field goal if given the option. Now again, different situations could occur. Maybe you're down by 4. Kicking a field goal doesn't matter. It doesn't matter if you score 3 points and still lose. Okay. But that's it for geometry. So again, one homework assignment will be due, and then one will be optional for extra credit. All this will be due on Friday, May 1st, because that decision's been made. The week after that will just be catch-up time. Okay, thank you.